thanks for the introduction, Chelsea. I'm honored to be here to present the most recent results. I think this is it's been actually one of the few public presentation during the pandemic years, so I'll try to my best to present the results. So this title is Artificial Intelligence Approach for Estimating Dairy Methane Emissions. It's mostly about the published results in ESMT this year. So my co-authors, I really appreciate every single one of those co-authors here from Berkeley Lab and UC Riverside. So I made this slide this morning. I thought that this might be a little relevant because I usually do not introduce this type of background, but recently a lot of people are trying to apply machine learning or deep learning or just overall AI. So I try to link the background and training to this result. How this scientist actually turned this idea into estimating methane emissions, how it is possible. And I just want to mention that a little so that I think that it will help you understand the overall story here. So I got some training in environmental engineering. So mostly I spend my PhD in C and C++ coding to develop land surface model using numerical method, including finite difference method, all that. And then I spent a lot of time in spatial analysis. So that's one keyword there. And then I got training from Berkeley's Michael Jordan. He's known as the Michael Jordan of machine learning or AI. Took some classes for statistical learning. I basically took all the AI fundamentals. 2 decades ago, almost, there's no AI, but it was called statistical learning instead of machine learning. And then I did some data simulation using satellite data. So here's another keyword, satellite data here. Unfortunately, I worked more than a decade on atmospheric inverse modeling that includes a spatial inventory development. I think I did one of the first kind of work in developing oil and gas specific spatial inventory using well level data in 2013-14 period. I always try to improve as transport modeling. In particular, I'm using Whorf-Stilt model. I do a lot of hierarchical Bayesian method. So here are 2 keywords here, inventory and Bayesian. So the motivation from training experience is, I always had this question, is there any better way of developing bottom-up spatial inventory? Because, I had this skill sets of spatial analysis, some background in AI training, and then satellite data processing, and then inventory. I did a lot of work in developing inventory. So theory is the first step, actually, to make this possible. I just really curious about whether this is possible or not. So many of you already know about methane, but I directly, it mentioned the dairy methane in California. So 50% of dairy California total methane is from dairy methane. So, but it's very uncertain. So I worked on inverse modeling for now almost more than 12 years. I think it's still, dairy methane is very uncertain, even in California. So the statewide in total may converge among different studies. In particular, urban areas, I feel that Southern California, I see converging among many different studies, but the Central Valley in particular, there are a lot of discrepancy between inventory and top-down. So I feel really uncertain about the theory, which is the main source in San Joaquin Valley of California. Nationwide, I think about 20% dairy populations among US states this is California. So I thought that it's a better idea to start from California because it's a 20% total dairy populations in the US. So that's why I try to focus on California, as more specific to California, San Joaquin Valley. The state law mandate that we need to reduce the manure emissions by 2030 by 40%. So this is like another key motivation of this study. So San Joaquin Valley, many of you are from California, so I think you're very aware of the situation, that this is the state study domain. From recent spatial inventory paper from UC Riverside, it says 90% of the dairy methane is from San Joaquin Valley, California. Another big challenge is actually oil and gas is co-located with the dairies in California. So in the perspective of atmospheric inverse modeler, we need to separate oil and gas emissions from dairy emissions. So here we are looking southern San Joaquin Valley. If the center city is Bakersfield. So if you look at this, within this here, this is oil and gas wells. I didn't plot dairies, but there is all over the places. So if you want to focus on this box region, so you need to tell how much is coming from oil relative to dairy. That's something we should be able to say as a atmospheric inverse model. So that's a big question. Before I go further, I just would like to mention this paper in 2021. This is, I call it human inspection-based inventory. Basically, human on the Google map identified individual facilities. So I was co-authored on this paper. So AI is benchmarking this paper all the way to the end. So just, I'd like to mention this at the beginning. So human visual inspections, identifying dairies on a Google map is very costly. People say you can use or county or air quality or water quality district, they may have the spreadsheet that have information about the dairies locations, but it's been very, very difficult to use those data sets, obtain those data sets and utilize correctly with some reasonable confidence. So that's why Mark Lane et al. In this paper actually visually identify individual facilities on a Google map. So that's how they develop inventory. Another avenue is the state of California update the GIS database for land use. I think it's a couple or a few counties per year. So if you look at all San Joaquin Valley, it would take about 10 years to update all the counties. But the problem with that is probably Fresno County is a year-old data, but Kern County ended up being 10 years of data. So there are some discrepancies. Even if we have that total updated GIS database for land use, including dairy facilities, so you might have a huge discrepancy in update year within the San Joaquin Valley. So this is about 20-year-old dairy GIS data compiled by cells at all. It was compiled in 2009, but the data, underlying data is about 2004 and 2005, so almost 20 years old. But this has been used for the last 10 years in most of California's inverse modeling. Another big challenge, I had not realized that this being a really challenge, was that reviewing operating permits for herd size. There are many ways, but Methane et al. Actually reviewed the operating permits one by one. So, my colleague, the co-author in the paper, told me that likely this is the most expensive process. We have to visit operating permit. Note that the form may not be exactly the same, but I just took this from here, and it has address. We can match spatial information from there. Number of milking cows, so we can get reasonable number of cows in that facility. So then our job is we need to link that dairy address and herd size to the map. So that's how we develop spatially explicit inventory. So again, I'd like to mention that this is one of the most time-consuming process. So now, new approach we developed in this paper is artificial intelligence in very, very general term here. There are several levels to the exact architecture we used, but just for, I prefer using general term AI here, so, and scientific knowledge. So briefly, this AI technology is very similar to self-driving technology. So you have to separate pedestrian and buildings and road and cars and trees. So the same technology here. We can update the methane emissions with low cost, relatively low cost efforts. And then we have, I think this is important, actual potential for improvement. Along the years, I think in the future, we're gonna have a new technology, better AI, and better data. So it has a huge potential. At the end, actually, I will mention a piece of development we did this summer, but basically it improved the accuracy a lot by changing the setups and using a little different technology. So all AI is doing is just estimate herd size. AI's help is needed for herd size estimation. How do you do that? So we provide raw image from the National Agriculture Imagery Program, about 1 meter resolution. And then we also provide a mask. It's called ground truth mask to guide the AI, which one is dairy, which one is non-dairy. And then the AI's job is just predict unseen images, just separating dairy from non-dairy pixels. So the task of AI is actually estimate the probability of each of these pixels, whether it's belong to dairy facility or others, orchard or road buildings. So this little box has 50,000 pixels. So we have to estimate the probability for individual, but we have this image, this kind of image, about 300,000 images to process. The key question in this study design is related to which variable really correlate with the herd size. Probably people may think of farm area and others, but the knowledge really answers, because I've been looking at the dairy data for a long time. I've been only thinking about maybe the area of the facility will tell us the magnitude of the herd size. So I took a look at the sales data, and I saw some correlation, not strong. It's not hugely strong correlation, but I saw some possibility. Note that this area is the total facility area. This includes manure, lagoons, and other field, not only the buildings, the freestall barns, and so it includes whole dairy farm, but I got some hint from this one. So the target facility in this work is a little bit different. We only consider open lots and freestall farms. I think that this is really the important aspects of the study design, because these two facilities are where the cows are actually residing or living there. So they spend most of the time in these two facilities types. So more specifically, AI's task is to predict the area of open lots and freestall farms. The AI job just ends here. I would like to just mention the magnitude of the task AI has to undertake. So this is NAIP imagery for Tulare County only. Tulare County actually much larger than this, but I just cut off the Sierra foothill area there because there are no dairy facilities there. So if you take this size here, it looks like this, and then we process this size each individual tiles. So look at the magnitude of the image tiles. That's why human cannot do these jobs. We have to rely on AI. So San Joaquin Valley total is 316,000, almost 320,000 images. AI has to process and tell me whether one of the 320,000 images should look like this or should look like this. This is dairy and this is non-dairy. So human can do, but they will spend maybe 10 years or more. But we have a lot of, they may make a lot of mistakes. So one example of this image is segmentation. We call it segmentation in computer vision. So we have to separate this image into this type. Of course, this is binary classification. So just keep in mind that the magnitude of the jobs. If you look at the continental US, I think the areas will be 10 times or more images. So one example is raw image and ground truth and the predictions. As you can tell, the AI is doing pretty good job. So the best accuracy here is, I think it's about 91% accuracies. So as you can tell, oh, it looks like a 90% accuracy because you can, this is true value, but this just captures the true values by AI. So I said, I just keep using AI, but actually the real structure is, it's called Unet. It's a U type. So this is U shape one, but structure. So we did a lot of testing using different structures, different pre-trained model. We built a machine here using GPU graphics card and use this TensorFlow from Google. And what's important is actually the column here, non-dairy fractions. So when I had a reasonably good scores here, if you have to look at the scores here, we want to improve the scores here. And then the strategy was actually in the images, we had to include non-dairy images. So non-dairy image means that the image without any dairy. Because if you, the AI, when the AI processes 320,000 images, they look at totally non-dairy regions of total urban area, total avocado field and strawberry field and the lakes. So when we included the non-dairy fractions as about 30% of non-dairy images, it improved the scores. So we took this model structure and we use this in the prediction mode. To other technical details, I'll just skip this one. But if you're interested, you can take a look at the papers itself. So this is the first result, dairy facility size estimation. So these individual circles are the individual tiles about 300 meters by 300 meters. So it shows within each tile how much area is dairy. So as you can tell, this Tulare County is a lot of dairy facilities. So it captures overall the patterns in San Joaquin Valley. It's promising. And then we graded at 10 kilometer. Why 10 kilometer? Most of atmospheric inverse modeling use about 10 kilometer scale. And then that's what I'm going to use if I'm doing inversion using this spatial inventory. So this is typical spatial inventory look. So again, it looks reasonable to me, and that a lot of Tulare counties has the highest population in southern San Joaquin Valley. And this is really important aspect of the study. So I aggregated the predicted area by county. And the axis is predicted dairy area using the 320,000 images. AI never saw USDA county level populations. It's totally independent data sets. AI simply predicted it based on the training I supervised, and then I took the data sets from USDA. USDA data sets are at the county level, so that's the only way we can actually evaluate these models. Look at this, how tightly correlated between the two. My initial assumption is that their herd size has something to do with the area. When we use the freestall barns and open lots only, and at the county scale, the correlation is more than 95%. It suggests to me that this is the right approach to use AI to predict the spatial area of each facility and use that as weights to disentangle the county level population. Remember, the dairy population is only available at the county level in my approach. Of course, you can read from the operating permits, but that's the opposite of the whole idea of using AI here, right? Because we want to make it the process quick and simplified, right? So we took the USDA county level data sets and then we use area as a way to disaggregate the county level population into individual level, facility level, their herd size. At least at the county level, it works. It works great. Now, we have to evaluate our product against the Vista. Vista is simply a McLean et al.'s product. So this is at 10 kilometer. Again, this is inverse model, uses about 10 kilometer size. So this is the number of cows from Vista from this paper, and AI generated cow numbers. Again, the correlation is tight to 95%. And let's look at different ways. It's violin plots. It's just density plots. It looks very similar to me. And spatially, it looks very similar. You can scatter plot. It's because its correlation is 95%. So this suggests that AI, at least at 10 kilometer scale, AI is able to generate reasonable herd size comparable to human-generated count numbers. I think that's the key message here. Now, the goal is not the count numbers, actually. We want to go and take this to the emission levels. So again, 96% correlation with the VISTA at 10 kilometers. So I just added one more comparison, just double check. This CalGEM is called another model developed by LVNL. It's old one because its underlying data is about 15 to 20 years old, but still 80% correlations. The VISTA is at 96%. The VISTA is, personally, I believe this is the most accurate inventory available in California right now. It's tightly correlated. So density aspects very similar, and the VISTA maps and AI, the VISTA AI minus VISTA, there's just differences, some difference here. But I would like to point out that there is one misclassification. So AI says we have there is here actually VISTA. When human actually inspected it on a Google map, there is no there here, but AI says, oh, likely there is. So that's a typical misclassification. So I think this is something we have to improve in the future studies. So far we looked at a little aggregated level, and now we want to look at the facility scale. The x-axis here is their populations, and this is our AI model, or the deep learning model, and this is VISTA again. So just visually, it looks very similar, as we can see, there are a lot more count, a lot more density for small areas, but there are small facility, I mean, small number of facilities for larger areas. So well expected. So I did some more quantitative analysis called overlapping coefficient. Simply take the probability density and then just look at the ratios common area covered by both probability density divided by the whole union density. So what this tells us is there is 58% similarity between AI and VISTA in terms of when we compare the densities. So this is more quantitative analysis. So in other words, it's more likely similar than being different between AI and VISTA. So, but I'd like to emphasize here, it's a facility scale comparison. It's really hard to compare at the facility scales, but the overlapping coefficient tells us that it's similar than different. Because at the beginning, I told that I have worked on the atmospheric inverse modeling. So from that perspective, I'd like to take this invert development all the way to mixing ratio calculation using transport model. My real interest is how would AI generated emissions actually differ from human generated emissions in terms of mixing ratios, which is atmospheric concentration, methane. That's the key aspect of this study because we want to use this AI generated inventory in real world atmospheric inverse modeling. It's pretty tight, and I would just conclude if someone is doing reasonable inversion using two different inventory here, AI versus VISTA CA, it would yield almost identical posterior emission estimates. That's my conclusion from here. actually, I didn't go all the way to the inverse modeling, but given these differences here, I think day 2 inversion would just yield very similar or indistinguishable estimates, given the uncertainty in the posterior emissions. So we did the total their emissions is just showing that I think it's a very similar to the CARB's estimates and also the Vista CAs. So we did some Monte Carlo simulations here. So another useful applications of this work is actually we were able to identify large 90th percentile farms, and then we converted the emissions into biogas, and then we estimated about 83 gigagram methane per year may be reduced from just using anaerobic digester, just use the biogas or transfer to the traffic, transfer gas usage or other usages. So that's just showing one example of this whole application. So the conclusion is that we developed a low-cost framework for spatial theory inventory. It required this aerial images and then some AI technology and spatial analysis technique and knowledge itself. Particularly because we want to resemble the estimated or inferred images back into on a spatial domain, because we want to have spatial images. So a lot of disentangle and resemble processes. So it needs quite a bit of spatial analysis technique here. AI shows comparable performance to human visual inspection, about more than 90% correlations. Very encouraging result. Segmentation errors, I've shown one example, and that needs to be addressed in future work. One more slide. Possible future work is, as I mentioned at the beginning, new AI methods using new data and new technology. I think the technology is just keep developing, so we can catch up with that, and it will give us a better accuracy in the future. Another idea I'm thinking was multispectral images. Maybe thermal property of there is probably different from the surrounding areas. So thermal property satellite data as coarse resolution here, Landsat data here is about 30 meters near Madera, California. But even if it's a coarse resolution, I think it would provide some information towards a better accuracy. And then Landsat 8, maybe that's an example. It might add more. Still, coarse resolution is, we call it a multi-scale approach. So small scale and fine scale has its own property, and the coarser scale has its own property. I think it might help, but we have to see whether this is a good idea or not. And another thing is I'm working on is long-term dairy emissions. So now we have a 10 years plus year with satellite data or aerial images. We can see the long-term, evolution of the dairy facilities, national, regional, and globally, and application to other sectors. Maybe we can use this technique to or framework to natural gas facilities. So lastly, during summer, working with a student, we improved the predictions to more than 95%. As you can tell, this is really sharp raw image mass, the predictions. I'm a little bit excited about this, and so the message here is probably in the future with the better technology we might able to reach higher accuracy, but we'll see. I think I see potential, a lot of potential in this framework. I'll stop here.